Hello everyone, and welcome to our webinar entitled Compact and Efficient Automotive Radar Testing. My name is Jerry Carpenter. I'm a technology marketing expert. I'm joined in the studio today by my colleague Andreas Ebel. He's a systems development engineer specializing in microwave imaging. Okay, before we get into the presentation, let's take a quick look at the agenda. Good place to start is really with an overview of the current status of radar technology and the drivers behind that. Once we've dealt with that topic, we're going to get into how to test these new developments. And I shall hand over to my colleague Andreas, and he's going to tell you all about the latest development in testing technology, specifically benchtop testing, which is the system you see in front of you. Okay, well, a good place to start when we start to think about automotive radar is what's really driving the technology developments behind it. And naturally, it's autonomous driving. As automotive radar developers strive for ever higher levels of ADAS functionality, then this drives the technology into higher levels of complexity. If we take a look at the current status, we're in somewhere around level 2 to level 3. We've seen the first releases of level 2 and even level 3. And each one takes its own type of development in terms of the complexity and numbers of radars that are required to be implemented and embedded in today's vehicles. So, just focusing on where and when and what the functions of radars are on vehicles, there are three basic classifications. We have the short-range radar, which support functions like parking assist. There's mid-range radar for ADAS functions such as cross-traffic assistant, and there are long-range radars that support functions such as automatic lane control. Where are we today? Well, if we look at 4D imaging radar, there's a lot of interest in the current capability to produce images, and we're starting to approach the same capabilities to produce images as we have today with LiDAR. It's somewhere in the range of 100,000 detectable reflections. There's instantaneous high-resolution velocity information for every reflection, providing not only the information in 3Ds and spatial, but also this fourth dimension. We're starting to see the emergence of higher-order modulation schemes and different complex modulation schemes really to support immunity against interference, and we're going to take a closer look at that in a moment. And one of the other main developments is virtual apertures, which significantly increase the resolution achievable by radar sensors and the field of view. And it's not just the hardware that's moving forward. A lot of the signal processing behind the artificial intelligence signal processing is producing higher and higher quality 4D imaging radars. Okay, so if we try to map the different types of radar that are required to support ever higher levels of autonomous driving, from level 1 to level 5, and as we've seen already, we're somewhere around level 3 today, you can see different types of radar, different numbers of radar, increasing in complexity, higher orders of MIMO being used, and higher numbers of sensors that are required in order to achieve the implementations of different ADAS functions. Of course, this naturally creates challenges for the developer, but also the supplier of a test equipment manufacturer such as Rohde & Schwarz. And we're going to take a closer look at that. First, let's look at the frequency spectrum that's being used. Of course, the main kind of interest is in this band between 76 and 81 gigahertz, but it's not the only frequency. In-cabin functions are used in this 60 gigahertz band, and some are over the horizon in the future, maybe 4 or 5 years out. This D band around 130 gigahertz is of interest. But for the moment, the external radars that we're seeing in the near future being developed are really in this 76 to 81 gigahertz band. Okay, so we've already seen that the radars break down into short range, mid range, and far range. If we're looking at also the premium and standard radars, each of which has different capabilities, you can imagine that a short range radar needs higher bandwidth in order to achieve finer and finer spatial resolution, but it also needs wider field of view in the azimuth. So this table, I won't go into all the aspects, but it tries to map out by frequency range, by bandwidth, by the distance it can operate on, the range resolution, and the field of view, all the different types of radar technology that we're seeing on today's cars. A little look into the future. One of the big issues that car manufacturers and automotive radar developers are facing today is really that the functions themselves are becoming more and more critical. The consequences of compromised performance are becoming more and more serious. There's a higher and more dense RF environment on the car, so immunity is becoming a big issue. And one of the countermeasures against that is to use different types of modulation that are more robust against interference. Today, FMCW is a fairly standard type of modulation scheme implemented on radars, but as we progress in the future, PCMW and OFDM will be becoming increasingly common. And these different types of modulation have properties of immunity against interference. Okay, so that's really the state of play today with regards to radar technology and a quick glimpse into the future. Let's drill down a little bit into how these translate to challenges for a test equipment vendor. All these increases in complexity in terms of the bandwidth, the MIMO modulation, different complex modulation schemes, these all need to be emulated in the lab when the radar is being developed and validated, but also in a field environment as well. So naturally, a test equipment vendor must be able to emulate this environment. As we approach level 3 ADAS functions, then it becomes necessary to implement virtual integration and vehicle-in-the-loop validation test solutions. As we go to advanced R&D of automotive radar, it becomes increasingly important to emulate multiple moving objects. It's not just one object, the static moving objects, and emulate certain complex traffic scenarios electronically to stimulate the radar sensor. Each of these objects in itself must be characterized with certain parameters such as its distance from the sensor, its size in terms of the radar cross-section, its angular and azimuthal velocity, and its direction as well. And this trend will only continue. As we progress to higher and higher implementations of ADAS, then the expectation is this will become more and more demanding for a test equipment vendor, and he needs to put these type of solutions in the hands of the developer in the lab. Where are we today with the current state of play regarding test technology development? Well, we're starting to hit some of the barriers or limitations of current solutions because to, for example, test a lot of the level 3 functionality, we're starting to become impractical, the amount of physical miles you need to drive on a test track. So really all the development must take place in the lab before we go out onto the test track. So we need OTA, over-the-air sensor simulation. We need certain complex traffic scenarios in order to be represented. Azimuthal moving targets is really important, and increased ADAS capabilities. The test solutions that are available on the market today, historically, to do all this kind of testing, have been bulky, expensive, and fairly inflexible. But I'm happy to say today we're introducing a new solution that sets a new standard in affordability and also practicality. And my colleague Andreas is going to tell you all about that. Andreas.
Okay. Thanks a lot, Jerry. So now let's directly jump into what are the possibilities, how we can basically object a signal for the radar. And in general, we can define, okay, there are plenty of applications we can use. One here is, for example, a very simple use case, which is just like to test a component. So, or basically it's called functional testing. So this is when you want to test if your radar sensor can detect an echo, distinguish maybe between two targets, which are given at a specific distance or a specific angle. And Then the second scenario is about more like benchtop or scenario testing. And this is like to test further advanced scenarios, like a traffic scenario where you have multiple cars, or when you want to simulate an emergency braking system, or like an adaptive cruise control. And here you need to simulate then moving targets in the azimuth, in the range, like the radial velocity, and as well as also the target size. And here you can do like scenario testing you can do for one sensor or also for several sensors. And besides that, besides, let's say, the normal functional tests and also the benchtop and scenario tests, there are also like further when it comes to standardized products, we need to do hardware in the loop testing. And also, especially when we integrate later these sensors into a car, it's about vehicle in the loop testing. But as well for hardware in the loop scenario testing or vehicle in the loop testing, we're having specific webinars we've already recorded. And for that reason, we are not going to have a deeper look in this. And we will more focus today on functional tests and benchtop scenario testing. And when we talked about the applications, and when we have a look now into the solutions we can offer. So for functional testing, basically we can already do these tests only with one QAT100, which is an electronical steerable antenna array. What this means in detail, we are going to take a deeper look later. And then when we are talking about more advanced benchtop and scenario tests, here we require a digital backend like the ARIC 800A to stimulate these advanced scenarios. And when we look later into applications or use cases in hardware in the loop and vehicle in the loop, these typically then require also firmware, or the products are embedded into a whole software, and especially in vehicle in the loop, also in a whole hardware environment chain. So to start with, or to focus on functional tests, as said earlier, it's a rather very simple use case, because here we really want to see, okay, does the sensor detect the echo accordingly? Then maybe we want to also distinguish, or does the sensor distinguish between two targets which have a specific distance or a specific angle? And talking about the angle, it's also about, we want to test the angular separations of the radar sensor. And how this is done, we are going to show you later. And then when we talk about scenario testing, so scenario testing, it's like stimulating more complex scenarios with multiple cars, bikes, and so on, like set emergency braking, NCAP scenarios, adaptive cruise control. And again, here it's about stimulating the targets in azimuth, in the range, the radial velocity, and also the target size. And depending on the scenario, we need a different setup depending on the range we want to look at. So we can start with scenario testing already, like with one QAT100 and the backend, like the ARIC, or we also can do it like up to 5 QATs to have a great field of view. All right. So having talked a little bit about the QAT100, let's take a deeper look into how the product is set up and what it makes so unique, especially for functional tests and later then also for scenario and benchtop tests. In general, we can say there are two, or that the QAT100 is really the first electronical steerable antenna array, which is designed for stimulating radar sensors or automotive radar sensors in the range from 76 up to 81 gigahertz. And to be able to stimulate the targets from the certain angular direction, normally other front ends traditionally need to be moved mechanically. And that's not the case with the QAT100. because the QAT100 has small antenna arrays in the front panel of the device. And here we are differentiating between two different hardware or front-end setups. The first setup is basically the so-called CMO front-end, and this front-end is consisting of 96 transmit and 5 receiving antennas. And this allows us to stimulate up to 4 echoes from different directions. And the CMO front-end can also be equipped with an additional transmitter line. And this then doubles the amount of IF paths and the supported objects. So for CMO sensors, we can stimulate up to 8 echoes from different directions. And then, as Jerry mentioned earlier, MIMO sensors become more and more popular. For sure, we also have newly now MIMO front end. We call it internally equipped with QAT-B21. And the difference here is the MIMO front end consists about 96 receiving and 96 transmitting antennas. And these are coupled into pairs to fulfill the MIMO requirements. And this then allows us to basically stimulate 4 echoes from different directions. And the MIMO front end is basically, it's optimized for minimum phase error. And for that reason, we can validate MIMO radars due to the improved spatial resolution of the echo we have in the kind of like 3-dimensional space. So now, having discussed the QAT100, so what are the advantages that the QAT100 has over the traditional mechanical approach? And the first thing is really, we don't need any mechanical movement here. As mentioned, due to its switchable transmit antennas, we can ensure a high resolution, high speed, and also high repeatability. And these electronic switching antennas, it doesn't cause any wear and tear or in general moving parts. So we have really the 4 gigahertz instantaneous bandwidth, and which ensures all, let's say, all automotive radars which are on the market now. And thanks to all the no mechanical movement, to the switchable antennas, we are totally immune to vibration, and we can really provide results that are very precise and also repeatable. And besides that, as seen earlier, the QAT100, it can be used as a standalone product. It can also be used with the back end. It can be used with several products aligned with each other. So here we are having really a very scalable solution that supports different scenarios. And when you combine, for example, multiple QATs 100, you increase the field of view. And last but not least, we are also having a shielded environment with reduced reflections and multipath effects. So here we are having a separately shielding system that provides nearly no interference or interference-free RF environment, which is perfectly suited for testing the base functions and also the scenarios. And on top of that, the small antennas, they are covered with a clean RF front end, which has a very low RCS. So this is reducing then the noise floor and suppressing close range targets, and also suppressing potential multipath reflections. So having talked a little bit about the different 2 versions of the QAT100 front end, let's have a deeper look how these front ends are set up specifically. So here we are looking now into an CMO radar system, which has an additional or a second transmitting line. And the instrument here is basically divided, or each line is divided into 4 segments. So for 2 lines in total, 8 segments. And these are controlled then by a transmitting circuit. And depending on the transmitting circuit, each segment has then also a receiving circuit. And this then controls up to, or per line 96 transmitting antennas, and in total for 2 lines 192 antennas. And when we look now into a simulation, how this is done, basically we are looking now into the segment A, segment B. These are controlled specifically. And for one line, we can then just like move the target from one side to the other side and back again. And when we are having like a second independent line, then this basically allows us also to start across the environment to simulate a second target on top. All right, so having had a look into the CMO front end, let's look how it's done for the MIMO front end. So the MIMO front end is divided into 4 segments. Each of them is also then controlled by a specific transmitting circuit. And here then each line has the same amount as the transmitter circuit has also for the receiving part. And due to that, then we can ensure that we have coupled each transmitting with receiving antenna. And then this means here we can control then 96 transmitting antennas. And as we have just seen now for the CMO front end earlier, we had this cross-sectional functions. Basically, this is something we can also do with a MIMO front end. In this case, we are then limited to the different segments, but nevertheless, we can also kind of simulate crossing targets here. And also important to mention here, this is basically with no time loss in between possible. All right, so as we have discussed earlier about functional testing and the QAT100 as a standalone product, and this can be ensured with analog step delay line. So here you see the back end of the instrument. You see for the CMO front end, you see the upper part, the transmitting line. You see the lower part of transmitting line. And in the middle, we are having like 2 B5 or 2 independent analog step delay lines put in. So what's the huge benefit of that? Basically, as mentioned, it enables the QAT100 to use as a kind of standalone mode. And we can simulate echoes from 2 meter till 13 meter only with the analog step delay line. But on top of that, we can basically also extend the simulating or stimulating line when we add expanded, or we can expand it when we add fiber optic cables. And on top of that, we can basically also take 2 analog step delay lines, put them behind each other, and then we can stimulate not 2 till 13 meter. Then it's like stimulating 2 till 26 meters. Or depending on the, with an analog delay line, like we are having here, like for 23 meters, then we are basically talking about 23 till 48 meters, roundabout. And the supported step size here is about 0.1 meter. And currently, there's no Doppler simulation possible. But if you have any requirements regarding Doppler simulation, please feel free to ask us anytime. All right, now having talked about the analog step delay line itself, let's take a look at the field of view and the angular resolution we can achieve. So here we see a MIMO front end of the QAT100. And basically the instrument is 351 millimeters wide, and each antenna is about 3.7 millimeters besides from each other. And basically for the field of view range we can reach, we have this formula, and for the angular resolution we have also this mentioned formula. And this allows us to easily calculate, depending on the distance we are having from the sensor to the DOT or to the QAT100, to increase different field of view. range and also to reach a different resolution. Because what we have also seen in the past that some sensors also, we need to have like a little bit like 1 meter distance to get into the far field range of the sensor itself. And here we are very flexible to achieve it. And then, as quickly teased earlier, to have kind of like to create a shielding environment, we have the QATZ50, the shielding system. And you also see it here. The shielding system is about 50 centimeters long. It has a 10 degrees opening, and we can directly mount it to the QAT, on the other side to the sensor. And you can even also, when you are talking about vehicle in the loop, as you've seen here, you can detach it in front of. And it's also, we are having kind of extension lines if it's needed to extend to the far field. So to sum up, what are the features, the benefits we can offer with our radar test system? First of all, as described earlier, we really have the possibility to simulate the azimuth, the elevation without any mechanical movement. And due to that, we are fully immune to vibration. On top of that, also having, let's say, no mechanical movement included here, we can also stimulate very short distances. And this, again, very precise and repeatable. And we can all do this with 4 gigahertz instantaneous bandwidth across the scalable field of view. And when we combine this test system with the ARAG 800, then we increase its capabilities that we can stimulate multiple independent dynamic objects. And also with the ARAG 800, we are having a hardware in the loop interface via this open simulation interface. Also, there's a specific webinar from my colleagues about this open simulation interface. And all this makes the system really very scalable and is optimized for performance across the whole development or echo chain of the radar sensor development. And now, having teased earlier, especially functional tests, let's perform some practical demonstrations. So let's come now to our practical setup and our live measurements and demonstrations. For this reason here, I have a MIMO QAT 100 located with 2 analog step delay lines. We have the shielding system to reduce the interference measurements, and we are having our sensor of our typical MIMO sensor, which is used in cars. And here on top of that, we are doing the evaluation of the sensor itself. So when I play the sensor, you can see suddenly here, okay, we are having a lot of interferences. And by placing the sensor close to the shielding system, we can basically nearly reduce all reflection. For sure, better it would be to have the sensor placed a little bit in between. The QAT 100 is now controlled here via software. So here you see the overview of the software. We are now connecting to the QAT 100 itself. The software realizes or detects, okay, it's a MIMO QAT, and we are seeing here now the 96 different transmitting antennas and the different segments. Besides this, we have the possibility to change several parameters, which we will do now step by step. And right now, let's have a look how it looks like when we start different segments or different points. So here now we are in segment A, and as you can see, okay, we see on the left side, we can see that the sensor is detecting a signal we are playing it towards. The point of interest here is marked in yellow. And now let's get away from segment A and let's go to the other side. And then we are having the possibility, okay, we see that the signal is now on the other side. So now with that, we could basically provide the information, okay, the sensor is detecting a signal or the echo correctly or not. And besides that, we also have the possibility now to move this signal. And for that reason, let's run the signal across all antennas so that we are going to see the signal across its chain. As we have just seen, we did play the sensor, a signal across the whole antennas of the QAT100. And now let's go to one antenna and let's increase or decrease the distance of the signal to the sensor. So far, we have only simulated one signal to the sensor. In the next scenario, we are going to simulate two different scenarios to the sensor to give an indication about the angular separation of specific signals or targets. For this reason, we did kind of change the transmitter mode from the line mode, where we were controlling all segments, to a segmented mode where we are controlling now segment B and segment C. And now here you see in this scenario that we are basically showing two different targets and we can kind of separate them from each other. Besides being able to change the targets in azimuthal, we can again increase or decrease the distance of each individual target.
Thank you very much, Andreas. Okay, let's bring together all the learnings from today's webinar and summarize them. So as we have seen, there's a lot of developments in terms of radar technology in order to achieve higher and higher levels of autonomous driving. Radar sensors are not only getting more numerous in cars, but increasing in complexity with higher order modulation schemes, MIMO, and wider bandwidths, etc. This naturally translates to challenges for radar sensor developers, but also for test equipment vendors. What we need now is the ability to simulate complex moving object environments in a lab, but we also need functional testing. And as we've seen from Andreas already, this new benchtop minimums configuration really breaks down the barrier to ownership that previously didn't exist for those that wish to have an affordable and compact and efficient automotive radar sensor test. But without losing the capability to expand to encompass future requirements for testing even the most complex of automotive radar testing configurations, including hardware in the loop and vehicle in the loop. In summary, as we look towards the future, we're going to see this trend develop more and more. And as we get not only to a simple scenario testing, but to more and more functional testing about specific ADAS functions that we need to verify in the lab. Thank you very much for your time today. We trust that you found the webinar both informative and educational. If you wish to find out more, please visit our website or reach out to Roden Schwartz, where you can find a whole load of more information on this topic. Thanks and goodbye.